Everyone, good afternoon, good morning, depends on where you are. It's our pleasure to invite Dr. Su to give a talk on his topic. And first of all, Dr. Su, can you introduce yourself and then you can deep dive the topic? Thank you.
Yeah, sure. Hello everyone. I'm Xiaoshan Xu from you can see that University of Nebraska Lincoln. So I'm a condensed matter physicist, meaning that I study solids and a lot of materials. So today I'm going to talk about something not directly quantum computing or quantum information, but some material aspect or some material support of that. Okay. Um, I will say a couple of things about the University of Nebraska Lincoln at the end of my talk. Actually, that was sort of like the task my department gave us, every faculty when we go out and give a talk, which kind of show people, remind people where we are. Okay, so let's come back to the talk. So again, I'm condensed matter physicist. Some people also call us material physicist. Um, so today I'm going to talk about some material called the magnetoelectric. Okay, let me change my laser point. Certain material called the magnetoelectric multiferroics, and talk about um, in general how symmetry and topology is important, especially in the context of helping quantum computing and quantum information. Okay. So I'm going to divide my talk into 5 parts. This is an outline if you want. So first I'll talk about the motivation, right? What is multiferroics related to quantum computing, and introduce a sort of like hero of today, a special type of multiferroic material, hexagonal rare earth ferrite magnetite, which is something I spent really a long time studying. So I choose this to focus on, and talk about the very interesting, or to me wonderful effect, so-called magnetoelectric effect. How do we use electric signal to control magnetism? And show you the idea. We can use electric tweezer to sort of like clamp magnetism. Um, and one special interesting thing about this material is spin topology. Again, topology matters, and how to deal with small magnetism readout, and some discussion about future. Okay. All right. So let me start with something actually that is not my expertise, but I'm trying to do this the best I can. So in this context, for this audience, if you care about quantum computing, there are a few you can call the commercial system out there. Typically 3 different categories, depending on the physical mechanism behind them, right? First type is superconducting. If you Google quantum computer, chances are you see this picture or something similar, right? A lot of gold wires, you can see this gold color. And all of this is to minimize noise, to keep low temperature, because the mechanism behind, right? So superconducting circuits use superconductor. It's a wonderful kind of material. Also, condensed matter physicists studied that a lot and started this whole thing. The idea is that you have this entire microscopic solid as one quantum state, right? And you can make use of that as your qubit and all that. But it's super sensitive to magnetic field, and it really doesn't like any thermal noise. So that's kind of the physics wall if you want. And second type is trapped ions. If you think about ions or atoms, they're perfect, right? Every one of them are, if you have isotopic pure, then they are identical. You cannot distinguish them. So they're perfect for quantum information. although you have to handle them, so that handle or the so-called trap is where you have difficulty with. And it's very, very difficult to scale this up because you have to use a big system to handle a small atom, right? So just to go from 1 qubit to 2 it's a lot of work. It's very difficult to go to let's say thousands of qubits. And the third type is a photonic part. You use light or photon. It's a um, extremely stable per se, right? Because light does not interact with environment that much. On the other hand, it's probably the interaction is probably too weak. So if you want the light interact um, and carry out computing, that's a lot of work. So that's another kind of physics wall. So because of all this limitation, so people have been thinking about other possibilities. Not necessarily say to make them commercial tomorrow, but just some possibilities. So one of them is to use a spin system. Okay, spin is another natural quantum state that you can make use of to carry information to carry out computing. It's similar to the single atom, but again, how do you hold it, right? So this is one idea from condensed matter community. Maybe we can use a kind of material called the multiferroic material. I'll talk about the more detail later on. But the idea is in this material you can use electric control to manipulate their magnetic property. So that can defeat a lot of thermal noise and make the system many order magnitude energy efficient. So that's not only good from quantum computing, although good for even just normal computing. So it's one possibility that condensed matter physicists or material physicists can help. Okay. All right. So now let's dissect this terminology, multiferroics. It looks very complicated, right? Or hope not that intimidating, but it's actually not too bad. If you want to understand multiferroics, just have to understand single ferroics. The best example for single ferroics is called ferromagnets. Okay, or for most people, you just call it magnets, right? This is something that human beings have been studying for thousands of years, right? And we have been using this for many years, like in the ancient time for navigation, and because the Earth itself is a magnet, or ferromagnet if you want, to be more sort of like scientific. And you find the magnets right at home, everybody, on your fridge door, and we use magnetic media to store information. Nowadays, this is less and less popular in our laptops, but still in desktop and of course still dominant in data center because they are really the massive data storage media. And let's not forget in our motor generator, ferromagnets is probably the most important component there. So again, if we speaking about the scientific definition of ferromagnets or magnets, they have to carry some kind of we call dipole moment, or for most people north pole and south pole, right? That's how you define a bar magnet, or if you buy a bar magnet, they indicate that for you, north and so dipole, two poles, and they have to be switchable. You put this in the magnetic field, and you can reverse south and north pole. And we also know that by research in the past, I don't know, 1,000 years, we understand now this big dipole, north-south, comes from all these small, tiny dipoles on atoms from atomic scale. And if you go further, they also come from the from electrons. Right? Okay. So the other single ferroics, if you want, is ferroelectrics. So if you compare this picture and the picture I showed, it's almost identical, except I changed north, south to plus and minus, right? So this is basically electric dipole. So you have positive charge one side and negative charge the other side. And if you have something like this, electrically you have a dipole. And if this can be switchable, then you have a ferroelectrics, right? And also we know this, this big dipole comes from small dipole on the atomic scale. But there is a crucial difference. The ferroelectric dipole comes from atomic motion instead of electronic motion. Okay, so if you want, here's a ferroelectricity application that you may or may not be aware of, but we actually use it a lot, right? Memory, probably not that popular, but sensor, really popular. Ultrasound, vibration sensor, sonar, and actuator. And this is a material that can generate extremely fine tune of motion, like to the order of like a few atoms, that kind of precision. And we use this electro-optical modulator as a backbone of internet. So ferroelectrics is kind of you can say it's unsung hero. So idea about multiferroics is to combine those, right? Um, if you put them together, of course, you can have all the application of them together. But that's not the goal. The real magic is when you put two things together, you often have the effect of 1 + 1 is greater than 2, right? That's what we're looking for. So how does that happen? So in general, and we actually mentioned this, right? For magnet, you can apply a field, then switch the north and south poles. For electric dipole, you can apply field and again switch positive or negative. So that's inherent from the single ferroics. But if you think about multiferroics and the two things together, they couple, then you have this opportunity. Use a magnetic field to change its electric dipole, and electric field changes magnetic dipole. Particularly this possibility, it got people really excited. For the reason that I mentioned a little bit, because typically if you use electric signal, especially a voltage, to manipulate insulator, it does not cost much energy. Okay, and the magnetic signal most time is also more stable than the electric signal. So if you combine this, we call this multi-electric magnetoelectric effect. There's a lot of new things that we can do, including helping quantum computing. Okay, so um, if you remember the title, there are several keywords, right? I mentioned multiferroics. Hopefully now you have a good idea. I also mentioned the symmetry and topology, which is something I will come back to like again and again and again. Okay, but let me say this from a broad stroke. Okay, so how does even ferroelectricity and these ferroic properties are related to symmetry. This is first example. If you have positive charge one side, negative charge another side for a material, that just means it's not symmetrical anymore. We call this broken inversion symmetry or loss of inversion symmetry. And if you have a magnet or ferromagnet, north pole, south pole, that's actually kind of like you have the solenoid or coil, if you flow current in it, right? And we know that if you flow current in the opposite direction, the south and north will be reversed. So this is what we call time reversal symmetry breaking. And if we keep going, right, for many molecules, this is a good example. Also, you can use our left hand and right hand, and they have this something called chirality. And that kind of symmetry also is important for physical properties. Okay. So that's symmetry. Okay. What about topology? Topology is probably not a name that everybody is familiar with, but I give you this example, then you probably have an idea. So I guess most people played with or heard of it, Mobius strips, right? It's very strange kind of topology. If you follow this one side and you can sort of like go be able to access both sides, right? So this is a certain topology. I'm not going to define this, right? But the key is, unless you cut the strip, right, you're not going to change the topology. So if you have some property that's related to topology alone, it's going to be very stable. So um, a good example is this that people often use to indicate this. So this is a cup, right? And this is donuts. So you can do this dramatic change from cup to donuts. As long as you don't add a new hole or you don't close this hole, and topologically, or they have the same topology. If there's some property related to the topology, even if you do this dramatic change, that property is still there. Okay, so extremely stable, right? So again, I'm a condensed matter physicist. We study materials, and in material there are also good examples. So this is sort of like a kite cartoon of atomic arrangement. So every dot is an atom, um, and there are some defects here, the A and B. So A is called the edge dislocation, B is called screw dislocation. That name doesn't matter. And this you can see that it really takes a lot of it takes a change of entire solid if you want to remove this defect. So it's another example of why topology introduces stability. And this is an example actually I will talk about later. If you have a let's say magnets, north pole point this way, right? And magnet, part of a magnet, north pole point this way, in the same magnet. Then in the middle there's something called domain wall. So we call these domains, and you can see that this domain wall is you can move it, but unless you totally change one side or the other side, you cannot kill this magnetic domain wall. So it's another topological defect. Shows you how stable this is. Okay, so so that's the introduction about multiferroics and some got idea about why symmetry um, and uh, um, and topology is important. Now I want to get into real examples. I'm just going to focus on one material, and we're going to look at this same material, same structure again and again and again. Hopefully, you have some idea just from this example. Okay. And again, I studied this example for a long time, so I personally like this a lot of physics we can learn from this example. So this is if you want for any material or solid, right? We always start with chemical formula. So this is a chemical formula of R, which is rare earths, meaning these guys in the periodic table, and either iron or manganese. So I put this a slash here, and 3 oxygen. Okay, so that's a chemical formula. But for condensed matter physics or solid, this is not enough. Okay, we really care about the arrangement in something called a unit cell. So in solid or crystalline solid, um, um, the atoms are arranged in sort of like array style. So in other words, they have the smallest repeating unit. So as long as you know that smallest repeating unit, you know the entire solid. So this is why we always focus on, a limited number of atoms, then that's enough. And this is this is what we call unit cell or smallest unit for this particular material. Okay, so if you really want to know this material, let's dive into this structure. Okay, again, I'm going to show this many times. So hopefully at the end of this talk, have this some kind of impression in your head about it. So we said the rare earths, right? This is a layer material. So this is rare earth layer. Okay. Another rare earth layer, another rare earth layer. Okay. And that iron or manganese doesn't matter. Okay. And they also form a layer. And they're surrounded by oxygen. So this red balls are oxygens. Okay. And this oxygen form sort of like a local environment called trigonal bipyramid, and we'll come back to this in a little bit. Okay. So why is this material multiferroic? And now we can practice what we just talked about, right? Symmetry. Why we have a certain symmetry, then we can have certain properties, right? First, let's look at the structure again. Let's pay attention to this rare earth layer. At very high temperature, this rare earth layer is flat. Okay, you can see that, this is hexagon and all the atoms are on the same plane, so they're flat. But if you go to room temperature, cool it down a little bit, then this center will go up and the rest will go down. So that makes this kind of we call it buckling, but it doesn't matter. So make this layer not flat. You can already see that if you have a layer like this, then up and down are not symmetric anymore, right? And we say this is a broken inversion symmetry. Yeah. Again, spatially up and down are not the same. So inversion symmetry broken. So if up and down are not the same, right? So chances are one side has more positive, the other side has more negative. So this corresponds to there's a dipole, electric dipole, or polarization, doesn't matter, pointing this way. So this is the origin of ferroelectricity. So about magnetism, we'll come back to this, but let's do this quickly. Let's focus on these bold arrows going through this iron or manganese atoms. And you probably notice that this local environment, they have some kind of a tilt, which is indicated here. And these arrows on the oxygen, they indicate how this object, trigonal bipyramid, if you want, right, rotate. Okay, and here's more clear indication of that. So they rotate, but if you have iron in the middle, right, and has the tiny magnetic moment on it, and it's gonna rotate with that. So all of this together, you can see that this magnetic dipole, right, will have a net component along this vertical direction. So we call this weak ferromagnetism or canted antiferromagnetism. That doesn't matter. We'll come back to this in more details. Okay, so that's in a very quick way to say that because of broken symmetry and this is multiferroic material. Okay. Okay, so now let's dive into more details about ferroelectricity and magnetism. Okay, so I'm going to introduce you this diagram, and we'll be using this diagram throughout the talk. If you want to pay attention and follow me and understand this, it will be helpful for you to understand the rest of the talk. Okay, so this is a kind of a top view of this structure. Yeah, again, we have this hexagonal structure, so that have this hexagon, right? And these six I marked R are these six rare earth atom, and there's one R in the middle, right? So I use color. The blue one indicate up, and this down indicate this green color indicate down. Okay. In the future, if I don't have space, I'm gonna keep the color, but I will not keep this the up and down these marks. Okay, so I have six up and one down, so that basically represents this picture, right? And also I have three oxygen here, which also indicates this three oxygen. You can see they move outwards, right? So that's what these arrows means. Okay, so and these are all pictures. I think the idea is probably okay. So, but I want to show you some real data. So, if we look along this direction, okay, and you will see columns or these columns, and they are up, up, down, up, up, right? And that's exactly what you see here. This is a electron microscopy if you want. So we using this method, we actually can see atoms, okay, how they arrange. So this is a side view if you want, right? As I said, if you look this way, you'll see up, 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 down, up, up, down, right? And that's exactly what you see: up, up, down, up, up, down, up, up, down, up, up, down. Okay, and these bright rows are rare earths, or in this case, ytterbium. You don't have to worry about that too much. And this row is the iron rows. So this rows, and you don't see oxygen because they're too light. And iron is also a little dimmer because it's lighter than the rare earths. But anyway, this is direct visualization if you want, or evidence of what I just talked about. And one thing I do want to mention, and this, you know, this is again has to do with symmetry. So this is a hexagonal material, so you should have some kind of a six-fold symmetry, right? So one of them is in so-called domains. So I showed you this kind of a diagram if you want, right? A top view. So one down and six up, right? So that means we have more up than down. So polarization is up, okay? And in this case, oxygen goes this way. And you can understand that, right? Oxygen goes away from the center, so it's dragged down. So oxygen goes toward this, so they are pushed up, okay? So on the other hand, the oxygen does not have to go this way. It can go, again, because we have the um, uh, hexagonal structure will have six-fold symmetry. So you can rotate by 60 degree. You should still have the same material. Okay. So in this case, it goes toward these three. So these three are up, the rest are down. So now we have more down than up. So this is polarization down. And can rotate another 60 degree. So we're going away from these. So these are down and we have these up. So now you have more up than down again. So this is up. You can keep going. After you rotate 6 times, you come back to the original. Okay. So again, this is totally the result of symmetry. And we'll show you why this is interesting and important. Okay. Again, talking about symmetry, we said all of this based on this hexagonal symmetry. Um, in reality, that's the first thing we encounter, from experimentalist point of view, because um, if you just mix a rare earth like lutetium and iron and three, mix all of these elements together, let's say burn them in a furnace, you actually don't get the hexagonal structure. This is what you get, something more close to cubic. Okay. Um, so we have to play some trick to make those materials. Um, so because hexagonal rare earth ferrite, this material in reality does not exist in nature. It's sort of like a human-made material. So the trick we play is to grow this as a thin film on top of template. If you choose a template that has hexagonal symmetry, like this aluminum oxide, and you can make hexagonal rare earth ferrite. And in the future, later on, we find it does not have to be aluminum oxide. Can be platinum, and the strontium titanate and cobalt ferrite and YSD. But all of them actually are cubic material. But if you choose a certain orientation that has the symmetry, you can also do it. Okay, and this is how we do it. We use something called pulse laser deposition, and this is a diagram. And the detail doesn't matter. The idea is you start with a template, with the symmetry you want. We'll call the crystalline substrate, and you spray atoms on it, right? The atoms come from the pulsed laser. This laser pulse is extremely powerful, so it essentially evaporates everything, turns everything into atomic vapor, and then the atoms land on the substrate. They tend to follow the arrangement of substrate and then get the hexagonal arrangement. So this is one of our earliest work. So we started aluminum oxide. This is a surface, and this is an X-ray diffraction to show the structure, and also this is again electron microscopy just to demonstrate the arrangement. All right, so I said the ferroelectricity and magnetism, but as using a cartoon, but I do want to show you why we say that, right? From condensed matter physics research point of view. Again, just to um, um, remind ourselves why we know something is ferroelectric, why we know something is magnetic. So if you remember, we talk about this, right? If you want to demonstrate something ferroelectric, you have to be able to show this polarization needs to be switchable in the electric field, and that's what we did. So this is a certain specific material that we made for this data. Okay, and you can imagine this is the if you apply enough voltage to this point, this is a state you get in. So polarization down, so more down than up. And this side, it's opposite, right? If you apply low enough voltage, you can switch the polarization to this state. Okay. So what about magnetism? And this gets interesting, and this is also sort of like the key for magnetoelectric coupling. Okay, so all of this diagram I showed you, right? Again, hopefully you're now not totally unfamiliar with this. It shows you rare earths and shows you the oxygen. These are three oxygens. Okay, but does not show you the iron. If you look at this picture, you see actually iron is right underneath. Okay, so if we want to talk about magnetism, we can use a similar diagram, but instead of showing oxygen, we just show iron. Okay, so this picture basically mimics what we have here in the three-dimensional structure, right? So for this particular case, you have the iron pointing toward the center. Okay. And the other three also point toward the center. Okay. And this is also forced by symmetry, because of the hexagonal symmetry, all the irons, they have to form, have 120 degree with respect to each other. Okay. So that said, it does not have to be this way. If the iron flip the direction, okay, then they're also like 120 degree to each other. And totally fine. It's totally fine. Okay. So but you cannot just rotate freely in for the iron in the plane. So they're only this two direction because of something we call magnetic anisotropy. We'll talk about that in a moment. Okay. So again, this iron moment, dipole or this tiny magnet on iron has to be parallel, either parallel to this or anti-parallel to this. Okay. And we'll talk about why that is. So what's the consequence of that for ferromagnetism? Actually, it's quite a bit. Okay, so again, let's come look at this. In the past, we only care about whether they point in or point out, right? But now let's look at the vertical moment. We said a moment ago, right? Because of this rotation, and there's a little bit of a canting or sort of like a vertical moment, the component of this arrow. Okay, so again, if all this iron point inside, the moments sort of like cant up. Okay, so we have magnetization, total magnetization up. Okay, On the other hand, we also said, you know, the iron can all turn around, make a 180 degree with the same angle as this. You can imagine on this picture if we turn this arrows 100 degree, and then this arrow will point down. Okay, so that means magnetization is pointing down. Okay, so we actually have two cases depending on the iron this tiny magnet on iron is parallel to this arrow or anti-parallel. If they're parallel, no, okay, like this, the moment is pointing down. The total magnetic moment, or if you treat this as a bar magnet, the moment the north is down, south is up, right? But if they're anti-parallel, then it's the other way. North is up, south is down. And if you want, this is a formula that summarize what I just talked about. Okay. All right. So and again, that's all cartoon. And this idea, we want to show this. That's our job, our condensed matter physicist job, using experiment. It turns out because of this, this moment is so small. It's only coming from you know, tiny angle, so it's not that easy to measure. So we use some special way called X-ray magnetic circular dichroism. You don't have to know the detail. The idea is if you shine some light, photon, or in this case X-ray photon, use clockwise or counterclockwise way, and then they interact with the magnetization up and down. They show different absorptions. Okay, and that's what we got. Right, clockwise and counterclockwise, they show different absorption. And if you look at their difference, we call this a dichroism or contrast, right? And if you change magnetic field and track that, and you get this loop. Okay, and this is exactly what we were looking for. Remember, a moment ago we said this is how you convince people that these are magnetic. Okay, and again you can imagine, right, in this high positive magnetic field, here iron they're anti-parallel, and here they're parallel. Okay, okay, so I said a moment ago, I was going to explain this, right? I said one thing from symmetry is iron has to be this tiny magnet on iron. They have to have 120 degree with respect to each other, but also they can only be either parallel to this or anti-parallel to this. Okay, but why, right? This actually has to do with the bonding and the symmetry, local symmetry, of course, bonding between iron and oxygen. So so we have to learn what kind of bonding we have. You know, again, the iron local environment looks like this: iron surrounded by 5 oxygen, 1 up, 1 down, and 3 in the same plane. And this causes the electrons on iron to have these levels. So if we can measure this level, energy level, then we know the bonding. Okay, that's exactly what we did. We use something called X-ray. You don't have to memorize this X-ray absorption spectroscopy and measure this, and these are the number we found. And this is probably the yeah, again, you don't have to worry about this formula, and we can feed this into calculation. And it turns out when when the moment is along x direction, okay, then the energy is smaller. So that's exactly what we mean by the anisotropy. Okay. All right. So so that's a basic multiferroic property of this material. So if you want, we can recap a little bit, right? We basically say that this is a ferroelectric material and this is a magnetic material, and we give you the argument, theoretic argument, symmetry argument, and we show the experimental evidence, right? but that's really not what we want. What we really want is something called magnetoelectric coupling, and that's really the holy grail in this type of materials. Okay, and let's look at that. Okay, in order to understand that, let's revisit something we talk about, an idea called domains. But now let's get more serious about this. What do I mean by domains? So a unit cell like this is something we have seen many times already, right? A top view of the unit cell has hexagon, 6 up on the parameter and 1 down in the middle, and we have this oxygen moving this way. And again, we have more up than down, so polarization up, and oxygen displacement along this direction. If you only focus on this, we give this angle called phi O. This is 0, right? But we mentioned that there are 6 of these variations, right? This is another one, okay? Equals 1/3 of pi, yeah, and this is the angle. And you can derive the up and down, right, polarization. And if you have part of the material or solid going this way and part of the solid going this way, and we call this is one domain, this is another domain. And in between, we call them a domain wall. Again, let's remind ourselves, yeah, these are topological defects. They can be moved, but very hard to be removed, right? The elimination really requires changing, wipe out totally this domain or totally that domain. Okay, and in this type of material, I showed you this this diagram before, but now let's look at it in a different way, right? Imagine these are different domains. They're going to form this domain walls, and I said the domain walls are very stable. But imagine in the center when all the domain walls meet, and this is going to be super stable because you're going to have to wipe out all the other 6 domains in order to remove this so-called vortex or clover leaf structure. People give it many names. And again, this is not, you know, our imagination, right? This is a real material property. And here are the evidences. So this is an electron microscopy, and you can see very clearly this the clover-shaped structure. 3 dark means polarization up, 3 bright means polarization down. And if you look at them just using so-called atomic force microscopy, the height of um, the surface actually does not change very much. You know, height is about the same, but the wall is different. Okay, this is another way to look at it. Basically, look at the conductivity of this, right? So this particular part, the vortex core is again totally a consequence of the symmetry. All right, so we said we want to talk about coupling between magnetism and electricity, right? But now let's look at it. So first, let's talk about a little bit sort of like a bad news, or at least people thought it was bad news at the beginning, right? So I mentioned that if we have domains like this, right? And if we look at the magnetic property, it can be like this or a different way, right? Which means that you rotate the iron by 180 degree. And this tool could give you a magnetization. Okay. And if you switch to a different electric domain, meaning that you rotate this by 60 degree, I would just talk about this. Phi O equals 1/3 pi. And you can also have the iron moment to follow. So iron angle is also 3 pi. So in this case, magnetization is still going down. So because these 2 angles are, parallel. So in other words, you have a ferroelectric domain wall, on 2 sides, they have different polarization or electric property, but on 2 sides, they have exactly the same magnetic property, right? So it looks like magnetic property does not care about electric property. If you look at this on this scale, okay, which is what people demonstrated on this particular material, lutetium scandium ferrite, hexagonal structure, of course. This is actually a solid. This is their sample. They demonstrated ferroelectricity by looking at the this loop, right, as we did, and magnetism by demonstrating this loop, as also we did. And then this is the clover-shaped domains as we talk about, right? No surprise so far. But when they look at the magnetic domains, and you see something different or something that that people did not want to see. Okay. And imagine, look at this scale. This is 2 micrometers, 20 micrometer. And if you demonstrate this, sorry, if you rescale this and put this into this picture, that's what you get here. So magnetic and electric domain have very different length scale, and you can see here, and even if you zoom in, you see the same thing. The magnetic domains probably do not care about ferroelectric domains. So this is what we call decoupling of domains between or magnetization or polarization. Okay. But that's not the whole story. It turns out the real story is actually more interesting than that. Okay. If we look at this a little bit more detail about the so-called domain walls. Okay. Again, right? So we have one domain here, we have another domain here. Now let's look at the domain wall. Okay. So here I use this arrow to represent the arrow of this oxygen displacement. Okay. And so on the right-hand side, they all point to the right. On the left-hand side, right, this domain, they point this angle here. So one thing we all know that the electric domain wall, ferroelectric domain wall, if you want, is very narrow. It's almost atomic size because it has to do with structure. Okay, so you almost have the abrupt change of this arrow. Okay, but for magnetic, it's actually different. Okay, far away from the wall, as we mentioned, the iron can follow this. The moment follows this displacement, right? The moment follows this. Or in other words, you can see this big arrow is parallel to this, and this big arrow is parallel to this. But in the middle, something weird will happen, you know, um, because because the magnetic domain wall typically is very wide. This just have to do with if you have a abrupt change at here at just too much energy. Okay. And because of this mismatch, you can see that on the side, right? On the side, you have one kind of domain, but in the middle, they're not totally aligned. So this is what causes, this is the consequence. So magnetic moment is large on the side, but gets smaller and smaller in the middle. Okay. So if you create a ferroelectric domain wall, you actually can change pretty substantially of the moment of the magnetic property in the middle. Okay. And again, this is a cartoon, right? This is the idea. I want to demonstrate that using our experiment. So the idea is we're gonna generate ferroelectric domain wall and see what happens. Okay. Remember we showed this, right? This is the so-called ferroelectric loop. Here, in this point 1, you have all the every unit cell that has a polarization down. Okay. Here in the point 3, you have all the electric unit cell that has polarization up. So because these are unified, right? So magnetic system is happy because they can follow. If this is homogeneous, magnetic system can follow as a homogeneous case. But for the pole 2 and 4, and this is what happens. All the moments have to add up to be 0, right? So that means there's a lot of up and down, right? So every time you switch between up and down, as we talked about a moment ago, right? The magnetic system is unhappy, or they're too busy to follow this, or they're not good enough to follow the change. So they have a little less moment here. Okay. And so you can count if there's a lot of up and down in the end, this is what you get, right? So total moment, you can see that is quite different in this case. And that's exactly what we saw here. So we measured their moment using, at 1 and 3, they're pretty similar. 2 and 4, they're not exactly the same, right? So this one evidence. There's another evidence that is not ferrite, so it's not iron. I said you can also have manganese in there to replace iron. If you do that, it's quite interesting. If you do that, um, the stable case is actually this moment and this, they are perpendicular to each other. So in the domain, in the big domain, far away from domain, we'll actually have a little moment, and around domain you have much bigger moment. Okay, and that's exactly what we see here in the experiment, right? And this is a sample or the film, right? With basically the height. You don't see anything, right? But if you use something called piezo force microscopy or PFM, and you see some of them have polarization up, some of them have polarization down, and these in the middle, right, are what we call domain walls, right? And if you look at the magnetic property, oh, it's quite interesting, right? The signal, the white means high, or and the black means low, basically concentrated along the domain walls. You can see that, right? And if you want to highlight this is a cartoon of this. So that's exactly the idea you see here. Along the domain, if you generate the domain wall, and then you actually can immediately make something from non-magnetic to magnetic along the domain wall, and basically given by these lines. So this is basically the idea about coupling, and what we can talk about how to make use of that as in the outlook in a moment. Then go back several times. These moments are very small, so it's very difficult to measure. So fortunately, it looks like we find that's all for what I have. We have did. So have done. So here is sort of like um, um, way forward, or putting this together. So one of the easy application, or something that we can make use of this property of material, is to use the Van Wall magnetoelectric coupling. You can imagine if you have a pair of domain walls, polarization up and polarization down, and in the middle you have polarization and sorry up on the side and down in the middle, and you have these domain walls, right? That's all normal in the sense of ferroelectric. But remember, we said the magnetic domain walls are much, much wider. So all we have to do is to make the middle thin enough, that is comparable to magnetic domain wall. So essentially, we can use the two ferroelectric domain to generate or to determine or to decide or to control the magnetism in the middle. Okay, we call this ferroelectric tweezer. If you just to help you, give you sort of like a visualization in your head. Um, in this case, so the magnetic property can be controlled by applying electric field, right? Um, and and you can log this using the domain walls. All right, and there's actually more to play. This is going a little bit more wild. Um, about topology. For example, as we mentioned, we can make use of the imperfection of the material, something called screw dislocation. So arrangement of atoms like this, which we see in the experiment, and this certainly can anchor or pin down certain magnetic materials state. All right, so I think that's all. As I said, this is what my department or my place want me to do every time I give a talk outside, to remind ourselves where we are. So Nebraska or UNL, it's pretty much at the center of a United States map, if you want, right? Or I'm not sure if this is center of mass. You can probably do some mathematical calculation, but it's pretty close. Okay. So we all these arrows shows our the place that we often oh, this is actually not right. This is a um um this is the national user facilities that we often use. So we are in the middle, so we're actually about the same distance to almost everywhere. We do have a pretty active research also in addition to this and outside too. All right, so um now let me acknowledge all the people who contributed to the work I've talked about, from University of Nebraska, Washington University, Fudan University, Temple University, Rutgers, Bremen College, and many national labs, Oak Ridge, Oregon, Berkeley, and Canadian. So the name in bold font are the postdoc and the students. Everyone else are basically PIs or my peers. And finally, I want to thank moderator and thank the host, and thank you all for your attention.
Thank you, Dr. Su, for the great talk. And I saw a question from Ron regarding to the slide showing a form of chemical vapor deposition using a strong laser. Is gravity the force that settles the vapor onto the seed material? Or maybe Ron, can you unmute and ask?
Yeah, I know what the question is. It's this, right?
Correct, yeah.
Yeah. So this is what, yeah, I can say, since you asked, I can say a few more words about this. This is called pulse laser deposition. So essentially you start with a target, solid target, which is the idea to introduce all the chemical elements in there. Okay, so it does not have to be in the same kind of crystal structure, as long as you have the correct proportion of elements. And because laser is so energetic, so one pulse can basically evaporize a small fraction of the surface and turn everything, like as I said, into atomic vapor. And then this is a substrate. So basically atomic vapor these atoms will land on the substrate. And substrate is also heated, and there are other ways to do that. And then atoms basically sort of like undergo the self-assembly, guided by the substrate, of course. If you do it right, you can get the structure you want. This is the trick we play to make something that does not exist in nature. For example, this hexagonal lutetium ferrite. Yeah.
So the atoms can float up and attach to the substrate?
Yeah, exactly. Yeah. If you look at this process, maybe you can probably learn something on the internet. It's pretty spectacular, almost like fireworks. One laser hit on this, it generates something called plume. The size of the plume is actually I have some indication here, but the real size of balloon is actually bigger than the distance from the target to the substrate. So you actually can see that by eye because there's a lot of ionization, all the optical process going to. Yeah. All because of the energy density of the laser pulse is very high.
And Is this sort of apparatus available at your university? Can you grow your own material?
Oh yeah, I have two of this kind of setups. Yes.
Awesome. Seems like a great toy. Thanks.
Yeah, very useful toy for us to play with new materials, especially some, like I said, something that does not exist in nature. We can try to make it.
I noticed Jordan, he has a question.
Hi, can you explain the differences and the benefits of plasma vapor deposition from the post-laser deposition method?
In a sense, this is also plasma, I would say. It's just we use laser to generate the plasma. Okay, so because the laser not only I mentioned that, right, evaporize everything into atomic vapor, it actually is more intense than that. So on the same time, also ionize the laser, the atoms, and generate ions. So in reality, you do have I mentioned this, the spectacular plume, like fireworks. That's because of the, charging, discharging, all the process. Okay, but I know what you're talking about. You're talking about probably sputtering. So so in that case, people ionize certain atoms like argon, and then you accelerate that using electric field, and use that to bombard the target, and hit the atoms out and do the similar things. Um, um, I would say pulse laser deposition is a cleaner, right? Because all you have on top of your target is a laser pulse. Once the interaction is finished, it's gone. For a sputtering case, argon ion sputtering case, for example, you use real atoms to hit the target and hope to knock out some other atoms. So argon, of course, is inert. You can get it out, but still, um, it is something real, right? But laser after the interaction is totally gone. It's just a package of energy, right? So pulse laser deposition in this sense is more versatile. Yeah. Of course, people use our sputtering to do a lot of good things too. Yeah.
Does the type of doping obviously would have to do with the tool you're using for the deposition and the doping, and because I know there's more, right, than chemical vapor deposition. There's quite a few different tools people use, correct?
Oh, yeah. If you want, there are basically two types. One is chemical vapor. The other is a physical vapor. So what we are using here belongs to physical vapor. So chemical vapor deposition, basically you start with if you want to introduce a certain elements, you basically have a molecular holder. You put that element in the certain molecules and you feed it into your chamber, and then it undergoes chemical reaction. Then the organic part gets evaporated, and you have this inorganic part remain. So and get your whatever material you want. Um, but here you don't introduce anything. Not only the argon ion. So this make this probably the most versatile tool. But of course, this is also more expensive than chemical vapor deposition.
Thank you.
Yeah.
So, if you're using this type of tool to build your sandwich, your different layers of the material you're testing with, like the rare earth layer and the FeO ferret oxide layers, are you like stopping this chamber, changing the the target sample, and then
Yeah.
just
So
repeating that process to get each layer built?
yeah. Good question. Okay. So we do that. I can show you that a little bit. But for your question, because this material this is a compound by itself. Okay. So once you put the lutetium, iron, and oxygen together and heat it up, they will have a so-called self-assembly. So they automatically form this this kind of structure. Okay, so in the target that we have here, okay, let me try to do. Oh yeah, here in the target we have here, it's actually just a. Oh, sorry. We just to keep the stoichiometry correct, you know, one portion of lutetium, one portion of iron, then certain portion of oxygen. And once they get them all on the substrate, and again, the substrate is heated, and they'll reorganize and form this structure. Okay, but your instinction is correct. We sometimes we often, well, we almost always have to do that, grow more than one layer, for the purpose of testing, for the purpose of stabilization and all that. So in this case, we do have to change target and grow another layer. Yeah.
Thanks. It's just fascinating that it would self-assemble.
Yeah,
It's
exactly.
a little mind-blowing that sort of complexity would just
Yeah,
self-assemble.
that's
Thank
why
you.
yeah, thank you. That's why I say you have to do it right. So there's certain condition that you have to satisfy, right? And that takes training and expertise. Yeah.
I noticed Terry has a question. Terry, can you unmute?
Oh, yeah. This was just a question that was popped up from one of your early slides because I've worked a little bit in some of the four-dimensional, three-dimensional space issues about topology.
Okay.
And I've always been intrigued by the difference between three-dimensional and four-dimensional transformations, especially on holes. They don't always work the same way in four-dimensional space.
That's right. Yes.
And your system seems to be four-dimensional with so I'm just curious.
I think we deal with three-dimensional. I myself never thought about four-dimensional. I think should be three-dimensional. Yeah. But if you have more insight, of course, we can discuss. Yeah.
Okay. The reason I mentioned some of the issues in particle physics, for instance, where you come up with the electric magnetic fields, they kind of wind up being four-dimensional and produce some interesting twists on how.
Okay. Yeah, these are all three. Yeah, definitely.
No,
You're definitely right.
you're
Yeah.
in three-dimensional real space. I know that.
Yeah, I mean real space. Yeah.
In terms of understanding the possible configuration space for the magnetic electric vectors combined in these
For
systems.
sure. Yes.
Well, it seems like that would be more naturally a four-dimensional space than three. And I've more than once seen some interesting oversimplifications when you go to four-dimensional space.
Absolutely. You're absolutely right. Yeah. What I present here are all three-dimensional real space, which is easier to understand. Yeah.
Okay, thanks.
No problem. Yeah, so hopefully give you some kind of a taste of what we do, condensed matter physicists, to play with the atoms, to play with the structure of them, you know, and of course eventually to produce the certain property that other people want, right? For example, yeah, that can help quantum computing. Yeah.
Ask your question, please.
It seems like William has a question.
Oh, please go ahead.
Sure. Dr. Zhu, I noticed all the Chinese collaborators and authors on your presentation.
Yes.
I
have a few.
Yeah, I'm a former U.S. Air Force officer.
Yes.
And so I watch the national security and defense space very closely. It's like you never get it out of your head because I served my time in the Air Force at Offutt Air Force Base, and I'm sure you know exactly where that is. My quick question is, once you have done what I did, which was go to nuclear war 6 times in exercises, you decide that peace is better than war. And so in my later years of my life, I've become a man of peace. And my quick question is, are you doing any sort of collaboration or exchange of information with colleagues in China? That would make me happy to hear that.
Yeah, you can see from the list. I have for example, Fudan University. This is a Chinese university. So I do that a lot in the past, especially. But the less to nowadays. But you probably are right, just by looking at the names, right? So what we do, as you can see, I showed you publication, publication, all basic research. Okay. So really, we need a collaboration with other people because I'm good at growing materials, but I'm not good at many other things. Yeah, sometimes growing material is not good enough. For example, all of this national labs, we have to go there to use their advanced facility to look at our materials. I showed you the transmission electron microscopy, and did not introduce the neutron diffraction, all that. Without those, we only have materials. You probably will say a good toy to play with, but what else, right? You have to understand what you do. So that's why collaboration is so important. Yeah.
Excellent. Thank you.
Yeah.
Hey, Terry, you have a question.
Mostly a comment. I just want to say this is really fascinating work, and the fact you're able to pull so many interesting properties out of these layers and just to get them to working is just intriguing. It feels like there's a lot of long-term potential. This is good basic research, the kind of stuff where people look and say, well, wait a minute, what could I do with that? And it just seems like there's a lot of things you could do with this that people have to think about just to understand it. But I was really impressed by the
Yeah. Thank you. Thank you. Thank you.
yeah, this is good stuff. This is
Yeah.
good stuff.
Yeah. Thank you.
Do you happen to know Dr. Ben Yu at San Diego by any chance?
Uh, not on top of my head. Yeah.
The only reason I ask is there's an Air Force project where they're looking into neuromorphic materials and trying to come up with very different ways of modeling neurology. And one
Oh,
of the things
okay.
that
Okay.
crossed my mind is that some of your whether they're quantum or not quantum, some of your materials could be of interest for that kind of emphasis on low energy, low temperature, energy efficient ways of mimicking neural systems.
Yeah. Yeah.
This just
Sure.
feels
Yeah.
like this could have some potential there.
Absolutely. Absolutely. So one of the of course I haven't touched that very much, but I'm aware um some people use ferroelectric domains.
Yeah.
There's a lot of physics behind that, but I don't want to mention the details to carry out neuromorphic computing. So people are trying toward that direction too. Yeah. Again, because now we can well I don't want to say make whatever we want, but we can make a lot of stuff based on people's need.
Yeah.
So there is a lot of potential. Yeah. But it takes time to do this, and also but every time you make a new material, you have to takes time to understand those. But a lot of potential and a lot of fun to doing those. Yeah.
Mm. Yeah, Dr. Yu, I think, is in like third or fourth year of a 5-year project on neuromorphic
I see.
materials.
I see. I
And
see.
but again, just so they're pretty mature in terms of which direction they're going and what they're working on. But uh, the contrast that myself and a lot of others talk about is just this huge disparity between claiming that giant server farms are all you need to imitate intelligent networks or quantum-like computing, and the idea that biological systems are a lot more efficient. So we're probably missing something in the solid state physics that enables much more efficient processing. And at some point, whether it's quantum or quasi-quantum may not make a difference, but
Yeah,
I
exactly.
love this kind of research you're doing because this is stuff that tickles in those areas and says, what can we do with this? without burning a whole lot of power, without burning a whole lot of energy. And these atomic molecular scale systems with complex states and interactions. Great stuff. So
yeah. Thank you.
I noticed Dr. Katina Penn raised his hand.
Yeah, I did. Thanks very much. I want to say first thanks to the professor for this very enlightening talk. I wonder first about the cost of making the synthetic materials, because potentially what you're doing basically, it's possible to replace the natural rare earth materials in the lab, but I suspect there might be a lot of cost in terms of energy to generate the synthetic topological materials. That is my first question. The second one is about the work that you're doing. It appears to be that you are doing work at the nanoscale. I wonder if topological material also could be developed at the mesoscale, and perhaps combining the nano and mesoscales to generate a similar kind of materials for much wider applications.
Yeah. Thank you very much. So let me maybe try to answer your first question first. So as we talk about, right, this is a pretty sophisticated method. So the advantage, of course, is you can make a lot of new stuff. At the same time, it is a pretty high cost method, just from the instrument point of view, right? The laser is expensive, and the whole chamber, you have to do everything correct. So that comes back to the point that one of our point that this is for basic research, right? To test the possibility whether we can make something, and also try to understand this a new thing that we make. So how to put this into mass production? We don't worry about that too much. Maybe that's certainly an important issue, but that's the next step, right? Whether you have this possibility of having this new thing and what this new thing is, that's the first question we have to answer. And these are all aimed to answer that layer of questions. I think you mentioned whether we can replace rare earths. In this case, probably, well, maybe yes, maybe not. We call this material rare earth ferrite or rare earth magnetite, but you can see what I have here, right? It do not have to be rare earth. So most of the rare earths, most of the time in the rare earth works, but you also can go to yttrium and scandium, right? And they are really much cheaper. Okay. Rare earth here is probably not the most important keywords here. Hexagonal is the most important keywords here. For the second question about going from nanoscale to mesoscale, it's not easy to go to. Well, although it's not impossible. You know, we grow film most of the time on the order of nanometer or tens of nanometers. But we can certainly, if we want, to go to something around a micrometer, or even multi-layer of that. But if we go there, the efficiency becomes really, really bad. So because if you make film that big, then the quality won't be as guaranteed as a smaller field. So I would prefer to go to chemical vapor deposition, which is much cheaper and much larger scale and much faster. And again, all the things we do, we focus on the very first step, right? Discover new material and make sure we understand what they are. The next step is not what we are focused on at this point. Yeah, mostly fundamental, basic research.
Yeah, thank you. Yeah, it's because I was thinking in terms of application in microchips and also long term, perhaps on electrical motors to increase the efficiency and reduce the heat losses.
Yeah,
but
exactly.
you're doing fundamental,
exactly.
yeah.
Yeah, so
you.
this is mostly a proof of principle. Yeah, want to see something whether it works, but whether it works with possibility of mass production is the next step. Yeah. Yeah. Thank you for the question.
I wanted to, I guess, add on that if you can share with us your thoughts on where the industry is with spintronics, because this is definitely an application like in the microelectronics memory and storage area where this has a lot of potential. There's been a lot of advancements, and the work you're doing absolutely fits into that. What do you feel is the bottleneck for mass adoption of spintronics?
Oh, wow, that's a big question. Okay, let me share my opinion. Again, this is totally just my opinion, right? Um, again, from our point of view, right, we focus on the possibility, proof of principle, whether something that um, from physics principle point of view can work. For the mass development deployment, you need to reduce the cost, right? And also another very important aspect is how do you fit into the current technology framework? Like how do you put everything on silicon, right? That's also another big question. So people are getting better and better these days. Again, after the proof of principle, and they can try to make the production cheaper and cheaper, and make the compatibility better and better. And if we really want to say spintronics application, some of them are already in there, right? The good example is it's a reader head from the giant magnetoelectric effect on our hard disk, and that's why the Nobel Prize was awarded. But whether this goes into or replace the current electronics, I think that's still not easy to do. Yeah.
Thank you.
That's just my opinion.
Do anyone have more questions?
Yes, I got another quick question, if it's okay. I just wonder if your team you work in is quite sophisticated area in physics, condensed matter. I just wonder if your team is working on the monopoles.
Oh, okay. Yeah, I'm aware of some of our peers or colleagues in other university that do work on magnetic monopoles. How do I say that? Conceptually, or my quick answer is no. But depending on how you understand the monopole or interpret the monopole. So if you go back to physics textbook, right, we always say that magnetic monopole does not exist, right? But now people do think about, let me actually use this example here. Yeah, here. Yeah, but now people actually borrow this this terminology to actually indicate something like this. So you have moments pointing together, and if you imagine, right, do the analogy with electric field, a positive here, negative here. So you generate some kind of a monopole here. But we never call it that way, and we also never study from that perspective. Okay. Again, just to clarify, right? The monopole that some of people in the condensed matter community study, it's a terminology we borrow from our textbook. Real monopoles still do not exist, right? But it does have a very interesting properties if you have this kind of kind of arrangement. And we're not focused on that yet. Maybe in the future we'll do something about that. Yeah.
Yeah, thank you. Thank you.
Yeah.
Teddy, it seems like you have a question. It seems that Terry asked domain monopoles, monopoles.
Sorry, I didn't quite catch that. Yeah, no, I was just commenting. I remember seeing quite a few articles, I think, about monopole pairs that they could simulate somehow, but I can't remember the article, so I'm fuzzy on whether I'm confusing electric with I think it was monopoles, but there was some interesting work done on that. Of course, none of them are true monopoles. That's an impossibility as far as we know, except for Valentine's Day decades ago. That was a notorious event. Wow. Yeah, it's a just fascinating area in that. I've also looked at some of the fractional charge domain wall. Domain wall boundaries are really cool area. You just can kind of bend the quantum mechanics in such fascinating ways at those boundaries. So
yeah, sure. Yeah.
Did you have any thoughts? This is unfair question completely. High temperature superconductors, but since you dabble in these domains and know that the turf generally, just any personal opinions about. No one's ever won a Nobel Prize for it yet, so I assume it's still technically unresolved.
Well, this is a holy grail in condensed matter community.
Oh yeah.
Right? So I don't have a good solution on that. Theoretically, it's possible, as everybody agree, but you have to do this in the real material.
Yeah.
That's the hard part, right? And people do predict, you do a certain material if the periodic table you can all make use of, including those non-stable elements, maybe there's a hope, but realistically, it's not even possible to test those, right? So, but who knows? Maybe someday some people find some magic combination of elements, then that can do the job. Just to put this into perspective, right? I studied something called complex oxide. Let me show you a picture, right? So we have 3 elements here, 2 metal and 1 oxygen. We call this complex oxide. But you can imagine there's so many entries in the periodic table, and the number of permutation, number of combination is, I don't know, it's probably infinite, right? We as a human being have just touched a very, very, very small possibility of those. So I don't know. The possibility is definitely there, but at least I'm not confident that I can touch that.
Like you say, there's so many things could be hidden. When they found out, I think it was a fairly common magnesium compound, a simple salt of some sort, had a very high temperature superconducting threshold, and it was kind of like,
that was
who
magnesium.
knew that? It just somebody had to
magnesium
test it.
boride. Yes, who knew that 2 component combined can give you superconductivity? Yeah. So yeah, so again, even for the complex oxide we play with, if you put this into the context of the whole periodic table, it's not that complex. There can be something more complex than this, which we haven't had the capability to study, right?
What are you wanting to do most next with your work? Where do you want to? What really intrigues you at this point?
Oh, I showed very quickly about the future, right? So we have this material particularly for a very long time. So we really went step by step. First, develop its ferroelectricity, the magnetism, then put them together, magnetoelectric coupling. The next step is really to show the tweezer effect that I demonstrated. So really make this further and further. Hopefully, like I said, some principle application. Yeah.
That does sound promising too, because you're playing with that combination of a couple things that people have not really, gone into that much depth. So that's intriguing. That's intriguing. Be interesting to see where that goes.
Yeah, yeah. We're also we're looking forward to the next result we get.
Cool.
Do anyone have more comments? I see Robert Baker. He wrote something. Indeed, since many
Well,
high.
I was just responding to the comment by Dave Chapman, pointing out that yes, actually, we have many world examples of high TC superconductors to play with and use. Have had that for what, 30 odd years, but we don't have any sort of single, even multiple theories to explain them and even potentially predict them theoretically since that time. So yes, Terry is right. There's no theoretical Nobel Prize for ITC superconductors yet. So here's a case where the experiment is way ahead of the theory. Sometimes, as in particle physics, when you had prediction of Higgs bosons and Higgs fields back around 1960 to 1965, that got way ahead of experiment, and it wasn't until maybe about 10, 15 years ago that we actually discovered the darn things for once. But here's the opposite situation. The experimenters like Professor Shu are way ahead of the theoreticians and still leading.
Well, just to be fair about this, the fact is that historically, like over most of the last several thousand years, experiments were way ahead of theory. And it's only since the late 1800s that theory has occasionally gotten ahead of experiment. So yeah, if you take a long view of this, the experimental phenomena have a habit of showing up before the theoretical explanations do. But I'll tell you this much: if we had a really good theory of superconductivity, which right now we have an okay theory, we would be able to sit down and systematically engineer high temperature superconductors. I mean, that's the advantage of having a really good theory, is that you can do things like that. Right this minute, it looks like my suspicion is that if you were to be able to predict the superconductive behavior of topologically ordered metamaterials, that would be the way to go in terms of making room temperature superconductors. But of course, we don't have any theories for any of that stuff, so it's not happening tomorrow.
Right.
Anyway, I really think this was a good talk, and thank you for giving it.
Yeah, so thank you.
Just quick comment there on the superconducting. Several years ago, there is a lot of speculations when Andre Geimai discovered the graphene. So I just wonder if people still work on graphene, trying to make it superconducting. But also on my earlier comment about the monopoles, which some people like Tokyo University and some other university in UK trying to develop these monopoles, quasi particles separating North and South Pole and so on. Those monopoles in spin ice potentially could be developed into superconductors. So although you're saying theoretical to some extent, but I think some people are trying to make some very basic experiment in this field.
Okay, yeah, sure. Well, let me say this. To me, the superconductivity, again, the holy grail in condensed matter physics, right? Extremely complicated phenomenon. If it's not the most complicated phenomenon in condensed matter physics.
Xiaoshan, I'll make my final comment. Someone said the importance of experimenters being way ahead of the theorists. It's not just experimentation. It's the ability to look at an experiment, notice a little effect and say, that's interesting. I think I should pay more attention to that. And I think that's one of the reasons why I like your research, because that's exactly what you're doing. You're saying that this
Thank
is
you.
interesting. Maybe we ought to dive into it. Maybe we ought to really dive into it. And you look at so many interesting things that have come up in physics, chemistry, just you name it. It's not just experimentation, it's the ability to pay attention and say something unusual that I can't explain is going on there. And that's where you get these really lovely dangling threads. You dive into them and all sorts of interesting things can pop out. So last comment, great talk, great talk.
All right. Thank you so much. Thank you so much.
Thank you.
Yeah.
Dr. Zhu, one more thing I wanted to pass along before the call-ins. If you ever make it up to Bellevue, which is just south of Omaha, make sure you visit Stella's Bar and Grill. They have fantastic cheeseburgers.
Okay.
And
Okay, all right. I'll note that down.
yeah, you'll love it. And when we had a road trip, we drove from just north of Denver all the way across Nebraska on I-80 to get there before they closed. So it's a really worthwhile restaurant. You'll love it.
All right. Thank you. Thank you.
Sure.
Those cheeseburgers sound so good. Maybe willing to travel up from Florida for them.
Well, yeah, if you go to Stella's, you'll never forget it.
Terry noticed you have a latest publication on January 22nd, 2026, persistent structural distortion for anticipated improper ferroelectricity in ultrafin.
Oh, yeah, yeah. That was our recent publication. So, yes.
Yes, yes. If you're interested to talk about it, just go ahead and schedule another meeting with us. We're still open in April, May, June.
I see. Oh, I can think about that. I can think
Sure.
about that. Yeah.
See you tomorrow, Helen.
See you tomorrow.
All right.
Yeah, and
Okay. Yeah.
so this is the end of the talk, and thank you for coming and for your engaged participation.
All right.
Yeah.
Thank you, everybody, for your
Thank you.
attention. Yeah.
And
Thank you,
please send me
everybody.
your slides.
Yeah, sure. I'll send it later.
So I will forward. Yeah.
Stop sharing.
Anyone question?
Bye.
Bye.
Thank you. Bye-bye.
Bye.